want to start off with what you see here. It's the summary of what we're going to be taking a look at. And you'll find this chart in your book, obviously. If you need to, I would even recommend printing it off, this one page off. That way you can see what everything is to begin with. Probably. It's a possibility. The thing with this is the information that had to have been obtained back in the BGC days, before graphing calculators. The reason is we can take a look at the function that we're working with and know what the function was and how to adjust it rather than doing out all the nasty calculations that can be done. Now, with computers and calculators, I mean, you can put the stuff in there and it does it the strong arm way and comes up with the actual functions. Okay. So, please keep that in mind. This is something that you definitely want to have the information for. So now, a lot of these things we have talked about, and we talked about this stuff last year, so I mean, it's not that we're running across anything new for you. Okay, come on, go. There it goes. So, knowing what the original function is extremely important. We've talked about the parent functions before and having that list in your head or your pictures, ideas of what the pictures are. So, you see something x squared. Do you know immediately in your head what that graph looks like? You do now. What is it? Yeah, just a parabola that opens up, right? Now, if I want to obtain a graph of that parabola with 3 added to it, what does that look like? Well, if we think about it in really general terms, you put something into x squared, you get that number out, then you have to add what to it? 3. So is that adding, what's that going to do? It's going to make it go up 3 because we put something in, we get a number out, now I got to go and add some more to it. So that's going to be a vertical shift of 3. So if I know what the parent function is, I know where things are automatically going to go. All I know now is that, hey, I just got to move that thing up 3 units. I know 0, 0 is going to be part of this. I know that 1, 1 is part of this, and negative 1, 1 is part of this. Okay? So, I identify those 3 points. I can either throw in the 2 and the negative 2, and I know that those points just go up how many units? 3. No big deal. Fairly easy. Vertical shift down. Okay? It says minus 4. Well, gee, what's that going to do to the actual function? Well, it's going to push it down. Okay. This seems logical. This seems very, very apparent, correct? Now, what about if I want to start moving things left to right? I got the x squared, and I see that I have x minus 2. So I put a number in, I subtract 2 from it, and I square it. Now, the last 2 instinctively went in the direction that we had anticipated upon. Okay? This goes in the opposite direction, does it not? If I need to, you guys will close the lids on these things. Okay? And pay attention up here. It doesn't do what we expected it to do, did it? It was the opposite direction. If I see x minus 2, I expected the 2 to go backwards, but it went which way? It went the opposite direction I anticipated on. Now, one of the things that comes up with this. No, the squared has nothing to do with that idea. If I go and have something along these lines, okay, I got f of x is going to be equal to our x squared. Okay, that is the same as y is equal to x squared, correct? Now, if I wanted to move it up, I could put, say, plus 2 over here, right? According to this, if I wanted to move what we had, I'd have to go y is equal to x minus 2 squared. Okay? Now, I'm going to do something here so that you can see how things really are applied. I'm going to rewrite this as y minus 2 is equal to x minus 2 squared. Now, you might remember me talking about this a long time ago in a place far, far away. Whenever you apply a shift, a movement to a point, you just think you got the coordinate, x, comma, y. If I add something to an x, if I add something to a y, it makes it get bigger, yes? If I subtract something from an x, subtract something from a y, it makes it get smaller, okay? It moves it down or to the left. When we apply that to an equation, it's always going to be the opposite. It's always going to be a y minus or an x minus. Okay? When we apply it up here to the coordinate, it's always an addition. We just put it in there and make it do the operation that it has. When we put it into the equation, it's always opposite. If you remember back a little earlier in the year when we were looking and trying to identify where a vertex was, and we had it that it was h minus k, right? And then it was like squared, and then but it had plus j out there, or h out there, whatever it is. No, it would have been x, would have been the h, yeah. So it would have been x minus h parentheses squared plus k. If I move that k to the other side, it goes to a minus, does it not? So whenever we're applying these things, it's always going to be that subtraction, the minus. It's an opposite reaction to what you would expect if you did that point with it. Now, the only reason why, when we were doing this before, when I did the up and down, or the left and right, or I should say the left and right, the up and down part, is because this value here was moved over here, and what sign was it? Plus. So it's not that this plus back here allows you to apply it and do what you expect on it. It's that it's been moved over to that side. So please keep that in mind when you end up having to deal with a transformation. Set up your original equation. They tell you what the transformation is. It's got to get applied like what we've got here. So now when we take a look at this, a horizontal shift to the right, it makes a little bit more sense to us. Okay? Because it applies to the equation as a subtraction. Okay? Backs up. Now, if I wanted to move this to the right, where would the value actually be? Would I want to change any of the output? Would I want to plug a number in, get the output, and come up with a new number? And then add it to it. Which won't work because that's what moves it up and down. If you take a look at this, when I want this here and I want to shift it this way, this point was up here at -2. It moves it to 4, right? If I want to push it this way, what number do I really need to put in there? If I want it pushed this way, okay, I want to move it this way 2 units. So I got to deal with the 2, right? But that 2 units means it's been moved 2 units to the right. What does that really do? If I go and just put, what did I have to do here? I got to add 2 to it, right? But if I want to do that same opposite in the equation. Okay? It takes time to wrap your brain around that one. The more you do it and the more you use it, the better off it is. I just keep telling students that whatever the shift is, apply it to the coordinate as you see it. Whatever it is for the function, it's always going to be x minus and y minus. Put the number in and then you can go. Okay. Now, that takes care of the shifts to the left, to the right. Now, can we combine horizontal shifts? Yeah. The nice thing is, I know what this function is going to be. I see I got x squared plus, or x plus 3 squared minus 5. I know I have a parabola to begin with. It's moved 3 units one way and 5 units the other way. So, if I would really want to think about this, I wouldn't think about this in terms of x plus 3. I would have to think about this as x minus negative 3. Now I know the direction that it's going to go. So if x is going to be negative 3, that means it's going to be moved 3 back. If I've got that minus 5 out there, that means it's going to go down 5. So I know that it's going to end up being right down here. Okay? So it got pushed over back this way 3 units after we went and rewrote it as 3, or as x minus negative 3, pushed it down. This is the fun stuff. Stretches and compressions. Okay? Now, the weird thing about this is a vertical stretch can lead to a horizontal compression. Think of a rubber bander. If you're holding onto that rubber bander and you pull it out, what happens? It shrinks down, right? If you've got it, you know, just sitting as a circle and you pick it up and you pull it out, what happens to the sides? Comes in. So when I'm looking at a vertical stretch in this case, what it really is doing, it's making things go faster, goes up quicker. So if I were to put negative 2 into here, I get a 2 out. But if I have a 2 out in front of it, it's going to be twice that amount. It's going to go up faster. Okay? Now, what happens if I wanted to shrink this? I could do it the same exact way, right? If I put in a negative 2, if I cut that thing into 1, cut it in half, that would move it to a negative 1. And if I put in a negative 1, I should get out what? 1. If I put in a negative 1 on the new one, where does it come up and hit? It hits it there at 1. So it's kind of difficult sometimes to tell was something compressed vertically or stretched horizontally, or you know which one it was. But it identifies just what they are. If I see this out in front, in general terms, if it's going to be applied to the x, it's going to be a coefficient on the x. If it's going to be applied to the y, would it be possible to multiply both sides by 2 and have it applied to the y? You got to see it. If I multiply both sides by 2, that doesn't really affect the x, does it? It applies to the y, because x is within that absolute value function. X is having something done to it. Okay. So, they do talk about the horizontal compression there, but like I said, horizontal compression, vertical stretch, kind of deals with that. When you're graphing this stuff, y is equal to 2 f of x. So f of x is a function given. What is it going to do? So, if I have a, here, let's start with that. Okay. Now, again, we gotta talk about this being in our minds. See, this is where I wish I could've had you watch that Einstein one, but you guys didn't want to watch Einstein. You've seen it bazillion times, okay? When Einstein was sitting here trying to figure out how things actually worked, he always had these mind games, correct? Okay. I find it helpful to be able to play that kind of a game when it comes to this stuff. So, I know what f of x is going to do, right? Granted, I don't see it. I can care less what it is. I just know that I do something and I get out this f of x function. Okay, it represents my output. If I put a 2 in front of it, what is that going to do? Well, f of x represents which variable on the coordinate plane? Y. F of x is output. Okay? So I did something, I got some function. Yeah, y is equal to this. Okay? So what they're doing here is they're saying, hey, I got some function. I don't care what the function is. I got some function. I put stuff in, I get stuff out. What is going to happen if I put a 2 in front of it? It's going to double. So if you think about it, for everything that I put in for x, I get something out for y. When I get that y out, what do I got to do? Double it. So now, is it going to shrink it? Is it going to make it go up? Or is it going to do that to it? The second one, it's just going to make it go up bigger, right? That would make sense, right? Now, what would happen if I do this here? I got the 3x. Okay? I'm putting in a number. Now I know when I'm doing a function, I put something in, something comes up somewhere along the line, right? So if I put this number in here, got something. I put in a number here, I got something. I put in another number over here, I got something. I put in another number over here, I got something. Okay? So I got my first one, my second one, my third one, my fourth one. Now, if I put that same something in here, but I gotta multiply it by 3, which one am I actually using? Am I really using my first one? Am I really using my second one? Or am I jumping all the way to my third one? Okay. Let's try that again. If I go here, do this. So now, if I want, I don't care what the function is, I do something and it's here, right? That's my starting point. And I don't think that that is going to record. Oh, it did record. Heck. So, it starts here. This is my f of x. Okay? Gives me this. Whatever I put in. So I put in my 1, I get that. I put in my 2, I say I get that. I put in my 3, I get that. I put in my 4, I end up and I get this out. Now, I am going to put this in now as f of 3x. Okay? So under normal circumstances, if I would push in 1, I'd get that, right? I'd put in 2, I'd get that. I'd put in 3, I'd get that. If I put in 4, I'd get that. So now I'm going to put in that 1. But that 1 is really going to jump me to where? To the output that I would get to 3. So, instead of having to go all the way out here, it's going to squish it in. It pulls it in. Okay? So, if I put in 1, that means I got to grab the output for 3, pulls this over this way, and we end up getting it faster. It's going to end up squishing, because this ends up going down here for where 1 is. Does that make sense? Okay. So really all that we're doing is just making things go quicker in that regard. So let's see if I can get myself out of this now. Go over here, go up there, and click right about there. So if I'm talking about that, which one of these would be representative here? Well, this would have to go with that, correct? Because this is what we originally started with, and now we're going just that much faster. Okay? It goes out, pulls it this way. Sort of kind of makes sense? It's the idea, if you can get a ballpark idea and get a feeling for what it's going to do, makes life a little bit easier. Reflections about the axes. Well, that's not that big of a deal. That's the plus and minus stuff, right? If I put something in, get something out, and then have the minus in front of it, well, it just makes it reflect across the x-axis, correct? Makes everything that was positive negative, everything that was negative positive. If I take a look at the next one, it talks about reflection about the y-axis. That means that my input was turned to negative. So I put something in, I get something out. Well, now this time when I put something in, I really have to take a look at its what? Opposite, which makes it go across the y-axis. Okay? And that gets us back to here, our summary of that. So, okay. Now, this is where I was kind of talking about the parent functions and understanding what those are. I got y is equal to the absolute value of x. Do we know what this looks like? I sincerely hope so. Okay. And that's just the big V goes down to the zero. Okay. A lot of times if you can identify the vertex for these things, or your critical points, like local minimums, local maximums, then you've got an idea of how to go and shift this graph. Okay? So, if this thing is supposed to be shifted 2 units to the left, okay, that's going to be on the x. Okay? How does that get applied? Well, they've got it as x plus 2, but if I want to move it to the left 2, that's negative 2, yes? Remember I said it's always got to get applied into the equation as x minus, y minus. So it's going to be x minus negative 2, which gets us to a positive. Okay. I want it to go shift up 3 units. Now we're in function notation. That's over here, so it's the opposite sign already. So we're good to go. If it says up 3 units, I just put in plus 3. And if I want it to go across the y-axis, what has to change? Well, the x has to go from positive to negative. That's the negative. Okay. That kind of gets us to when we're talking about combining graphing procedures. Now, the question is, do you know what the original function for this looks like? Well, I got some numbers, variables in the bottom. Numbers, variable, bottom, reciprocal function. Okay? That means that it's going to come this way, go down, go that. So that means we've got this function here. Comes in, goes down, goes up. That's what it looks like. We got some critical points that we can come up with. And the ones that I always like picking on are the easy ones, you know, like 1, 1, and 1, negative 1. Those are easy points to work with, 0, 0. Pick the easy stuff. So, I look at this and it says that I got x minus 2. 3's on top, 1 is out there. So, how in the world do I get to this? Well, it's kind of like deconstructing it. If I had to go and simplify this thing out and get it to where it was going to go, I'd have to pull that 3 out. So it kind of gives us an order of what we need to deal with. So, I need to multiply it by 3. That's the next step. Okay. Then I replace that, move it over. Then after I move it over, then I get to move it up. Do you have to do it in that order? Not always. I mean, could I go and move this thing over and then multiply everything by 3? Should work, right? about it in these three terms. So you can kind of add that as a little note onto that sheet when you've got it for functions. Do reflections first, compressions and stretches, then shifts. Okay. That way you've got kind of a consistent method for attacking